So far, you have learned some tricks to implement the particle filter and how to assess the accuracy of your filter. Now, I'll give you an overview of the code that you'll be using to complete your project. Let's first look at the file main.cpp. This file will run your particle filter, as well as measure its runtime and calculate the weighted error at each time step. The first thing you'll need to do is set the number of particles in your filter under this to-do comment. M is the number of particles to draw. Here, I have set the uncertainties for the different measurements that you'll be using. Next, the main function reads in the map data, the control data, and the observation data for each time step. In this for loop, you'll implement one step of your particle filter under this to-do comment here. At the end of each time step, you'll calculate and print out the weighted error. Finally, after your particle filter has gone through the entire driving sequence, the main function will calculate the runtime for your filter. And that's it for main.cpp. You will implement most of the particle filter code in particlefilter.cpp. This file contains all of the implementations of the functions of the particle filter class. Now, we'll go over each function you'll have to complete to finish the project. The first function you'll have to complete is init. This function takes as input a GPS position, an initial heading estimate, and an array of uncertainties for these measurements. It then should sample from a Gaussian distribution centered around these measurements to initialize all the particles. It should also initialize all particle weights to 1. You can look at the details for the particle struct in particlefilter.h. The particle filter class has an internal structure of particles that is updated, so nothing is returned from this function. The next function is prediction. This function takes as input the amount of time between time steps, the velocity and yaw rate measurement uncertainties, and the current time step velocity and yaw rate measurements. Using these measurements, it should update each particle's position estimates and account for sensor noise by adding Gaussian noise. Once again, you can add Gaussian noise by sampling from a Gaussian distribution with mean equal to the updated particle position and standard deviation equal to the standard deviation of the measurements. The data association function here takes as input two vectors of landmark OBS objects. You can find the definition for this struct in helperfunctions.h. This first vector is the predicted measurements between one particular particle and all of the map landmarks within sensor range. This other vector here is the actual landmark measurements gathered from the LiDAR. This function will perform nearest neighbor data association and assign each sensor observation the map landmark ID associated with it. Next, you'll need to complete the update weights function. This function takes the range of the sensor, the landmark measurement uncertainties, a vector of landmark measurements, and the map landmarks as input. The first thing you'll need to do here is to predict measurements to all the map landmarks within sensor range for each particle. Once you have these predicted landmark measurements, you can use the data association function you implemented to associate the sensor measurements to map landmarks. You'll need these associations to calculate the new weight of each particle by using the multivariate Gaussian probability density function we discussed in the lesson. Finally, you'll have to normalize these weights so that they'll be in the range 0 to 1, because next you will use these weights as probabilities for resampling. You're almost there. The next function is the resample function. You can use the weights of the particles in your particle filter and C++ standard library's discrete distribution function to update your particles to the Bayesian posterior distribution. Finally, you're at the last step. You'll evaluate your particle filter by calculating the weighted error. This function takes the ground truth position at a particular time step as input and calculates the weighted error of your particle filter using the weights of each particle. Feel free to check out the files helperfunction.h, map.h, and particlefilter.h if you're curious about the finer details of the code. To build and run your code, open a terminal and simply go to the localization particle filter home directory. Then type build.sh and then run.sh to run your particle filter. Now I'm handing it over to you. You have all the tools you'll need to complete the particle filter project. Have fun and see you on the other side.